In this lecture now, we want to finally look at the definition of entropy as it was introduced by Shannon in the context of information theory. So suppose we have a random variable x that takes values in a finite set A, so our usual setting, and the distribution of this random variable we denote by p. So we define the entropy of x, h of x, it is usually denoted as the sum over all elements of A, p of x equals A, times the negative logarithm of the probability that x equals A. And this can be rewritten in this form, or short, we can write it like this. We put 0 times log 0 as 0. So this is consistent because if this expression x log x goes to 0 when we let x go to 0. So what is the motivation behind this definition? Well, in the last lecture, we saw that this function here, minus logarithm of probability, can be seen as the information we gain from knowing that a random variable takes value A. But if we look at this expression now, well, that's just the expected value of this function here, right? Because we sum over all possible probabilities, all possible outcomes of the random variable, right, according to the probability of that outcome. So the entropy of a random variable is the in that interpretation, the expected gain in information with respect to the distribution of the random variable. Let's look at some basic properties of the entropy function. So first note that it's always non-negative, and that follows easily from the fact that we are using we're taking the negative logarithm of a probability, right? So that's a value between 0 and 1. Here, this is between 0 and 1. So the logarithm of this is negative, so we take in the negative logarithm. So we get a positive value, then multiply by non-negative probability and sum everything up. So this is clear. And we also have that h of x is 0 if and only if one of the values has probability 1. So one of the possible values has probability 1. And that also follows easily from the fact that these p's here, p of x equals a, that is a probability distribution. And it also kind of corresponds to the intuition that if one outcome is always certain, then we don't gain any information from that outcome, right? Because it does not give us any further information that we didn't have before. Next, we observe that h depends only on the distribution of x. So it's a function of the distribution. So it's a function that is defined for any finite probability vector, right? P equals P1 up to Pn, where all the Pi's are non-negative and sum to 1, right? So in this sense, we can also regard h as a function of such P, and simply write then h of P equals the sum of all Pi log Pi, and take the negative sum of this. So we will often, in this context, often write instead of hx, we write hp, right? And h for a random variable, we have hx equals hp, where p is the probability vector of the distribution of the random variable. It is also clear that h does not change when we permute the pi's, right? So if I change the order, let's say of p1 and pix, change those two values, then that doesn't affect h of p at all. So that's also called a symmetric function. We can also ask, when does the entropy assume the maximum value? Well, h is continuous, right? And as you can easily see from the definition, and it's defined on a compact set in the sense that it's defined for all probability vectors. So it must assume a maximum value. So where does it assume that? Well, one can figure that out analytically, but let's just look at some intuition. Maybe we can get some insights from that. So a random variable with finite values can be seen as a finite partition of the unit interval, so 0, 1. And we've seen from the discussion of information, the smaller an interval is, right? So the smaller the probability is, right? Here, let's say that's a small interval, the higher the information gain I get from the knowledge that a point drawn on the unit interval or in the unit interval is in that interval, is in that little interval here, right? So ideally, we would choose all small intervals, but we assume that now our a, so the number of intervals in the partition, is fixed. So for fixed a, that means for all probability vectors of a certain dimension, of a certain fixed dimension, right? So we cannot go on and just have arbitrarily small intervals. Let's say we just have 4 intervals, and then if we choose 3 small ones, then we inevitably end up with one very large interval, which then gives us very little information gain if we know that, gain the knowledge that our point is in this interval, right? But also this interval now has very large probability, so it will decrease the expected gain of information, that is the entropy, accordingly. And this should convince us that the highest possible, by just looking at symmetry now, right, that the highest possible entropy should occur when all the intervals here have the same size. And that is indeed true. So h of x is max when p1, so which is the probability distribution vector, is now equal to p2 is equal to pn. And one can show this using just a little bit of calculus. And here you can see this in a special case. This is the graph of the entropy function for a binary random variable with probability p1 minus p. So here we have x takes values in a 0, 1, and let's say p x equals 0 is p, and p of x equals 1 is 1 minus p. And here you have the according entropy of that distribution. And you see that for the equidistribution, 1/2, the entropy takes its maximum value 1. Remember that we use binary logarithms, so we get a value 1 here, because log 2 is 1. So once again, we have the logarithms we use are binary, so log 2 is 1, and hence we get the maximum value 1 here. Next, we introduce joint entropy. So that's a value for two random variables. So assume now x and y are random variables with values in some finite sets A and B, respectively. And the joint distribution of x, y is given by these values. So the probability that x is equal A and y equals B. And then we can define the joint entropy as follows. We just take it as essentially the expected value of the joint probabilities, right, of the negative logarithm of the joint probabilities. And I've written out that this is given as log p of the probability that x is equals A, y is equals B, right, and times the probability of this, and we sum this over all possible combinations of A and B. Right, so this is then written as h of x comma y. So x, h comma y, that's that denotes the joint entropy of x, y. So in this sense, the joint entropy is not really the entropy of two random variables, but of a single random variable, namely the random variable that we get if we refine the partition, right, that or join the two partitions that are induced by x and by y, right, by intersecting all the or taking all possible combinations and get a finite partition. So if you think of here are one random variable x, partitions like this, right, and then our random variable y, partitions like this, right. So this would be y, this would be x. Then the joint distribution assigns probabilities to each of these areas here now. So the refined partition, and it is the entropy of that new refined random variable that we're looking at here. That is the entropy of the joint entropy of the two variables. We can also define the conditional entropy of a random variable, so conditioned on another random variable. So h of x conditioned on y is the entropy of the random variable x, where we condition it on y being equal to b, and then average this over all possible values for y. So what does this formally look like? Hx condition on y is just the average, right? So the expected value of h of x, where this x now is conditioned on y being equal to b. So the value of y equal to b. So how is this defined now? So this value here, well, that just denotes the entropy of the distribution of x conditioned on y being equal to b. Namely, right, here's the formula. It's just we fix y as b, so to say, and now condition this kind of conditions and redistributes x, and now we just take the entropy of that redistributed variable, random variable x, and according to the usual formula, namely log of the probability times the probability. Now we can put all this together, so this formula and this formula, right? And so if we just plug in everything, we just obtain this line. But we can simplify this a little bit, because we see here, well, b doesn't occur in this sum, so we can just move this one over here, right? So we can move this term into this sum. But then we see we have the probability of y equals b times the probability of x equals a given y equals b. Right? But that's just the probability that x is equal to a and y equals b. Right? That's the joint probability for a and b. And then we have the usual logarithm of p, x equals a, condition on y being equal to b. Right? This comes from all the way down here. But now we look at this, well, that's just the expected value again of this function here over all possible xy's. There's a very nice connection between joint entropy and conditional entropy. Namely, if we interpret entropy as information gain, then this following equation makes sense intuitively. Namely, the information gain from knowing x and y, so the outcomes for both of them, should be the same as the information gain from knowing x plus the information gain from knowing y given x. Right? And that's indeed true. I mean, the following theorem, also called the chain rule for entropy, the joint entropy of x and y is equal to the entropy of x plus the entropy of y given x. And the proof is rather straightforward. You only have to use the fundamental identity for the logarithm, right? And you also observe that we can write the entropy of x as we can write this artificially as a double sum over all a, b, just plugging in all possible values for b here. But noting that this does not affect the value of this function here. So we just sum up over the finer partition, but still obtaining the same value. So you should probably sit down and just prove this using these two observations here. And then the proof is rather straightforward, but to familiarize yourself with these concepts of joint entropy and conditional entropy, it's actually a nice exercise just to work this out. So we can now put together all these properties we have observed so far of the entropy function and actually obtain an axiomatic description of entropy by just listing these properties. So in the following sense, so suppose H star is defined for any a-valued random variable where a is an arbitrary finite set of any possible finite cardinality, and H has the following properties. It's non-negative, right, for any possible random variable, and it takes the value 0 if and only if in the distribution one outcome is certain. As we observed before, this holds for the entropy function that we just defined, as do all the other properties that follow. But let's assume we have a possibly different function that also has these properties, namely it is continuous if we restrict it to a certain fixed a. So that means it is as a function of a certain probability vector of a fixed dimension, right? Then it's continuous, and it's also symmetric, and it takes its largest value for equidistributed x. And again, this notation here means that we fix a. So a is given as some a1 up to an, and then we can restrict H star to all random variables taking values in a, so it becomes a function defined on all probability vectors p1 up to pn. So we further require that this identity holds. So this may look a little bit suspicious, because it seems that we need to have defined entropy in order to define the joint entropy and the conditional entropy. But if you go look at the actual definition of joint entropy and conditional entropy, it actually only you needed to know the joint distribution. And as we noted, the entropy of the joint distribution, or the joint entropy of two random variables, is actually can be seen as the entropy of a single random variable that you obtain by refining the partitions induced by x and y together. So it's also a good exercise to go back, look at those definitions, right, for joint entropy and conditional entropy, and look that if we have a function that is actually defined on any a random variable, that we can use this to also then define these functions, right, in the sense as we did before. And then we also have property number 6, which we haven't explicitly observed yet of the entropy function, but which is very easy to see. So if we require that we extend the alphabet by one letter or one element, and we have an a-valued random variable, and y trivially extends this random variable in the following sense, it just for a, it just takes over the probabilities from x, and sets the probability that we see this additional element here to 0, right? In this sense, it trivially extends x. Then we don't change the entropy. This new random variable has the same or h star value that x had. So if this h star satisfies all these six properties, then one can show that there exists a real number lambda such that h star is just lambda times h. So these 6 properties fix the entropy up to a scalar multiple. And if we moreover require that h star of 1/2, 1/2, right, so the binary equidistribution is 1, as we observed before, is true for h, then we actually have everything fixed. Then h star must be equal to h.